The collision model theory, which underpins our understanding of reactions and reaction kinetics, is based upon the fact that molecules are going to collide, and they have to collide in order for them to be able to affect change in their bonding, either breaking bonds or forming bonds. So collisions have to occur, and some of those collisions are going to be more effective than others. What do we mean by that? Well, if two particles collide but they don't have the right amount of energy, they don't have sufficient energy, then they're not going to be able to break existing bonds or potentially form new ones. If they don't collide in the proper orientation, then they're not going to be set up right to be able to make the new connection, the new bond that is desirable. And so in order for a collision to be effective, you have to have these two things with the colliding particles in place. One, they have to be oriented to each other in a proper way. So it's kind of like taking two Lego bricks. If you put them top to top, right, they're not going to stick. But if you put them in the proper orientation, then the Lego bricks will be able to attach to one another and hold together. Secondly, you have to have sufficient energy involved in the collision. So just as if somebody taps your bumper with their car, your airbag probably won't deploy because there wasn't enough energy in that collision. But if they hit you going a little bit faster, then the airbag may deploy because there was sufficient energy in that collision to activate the mechanism in the airbag. So we talked about those two variables, the proper orientation. Here you can see an illustration showing that the chlorine atoms in green, if the lone chlorine atom collides with the molecule in the direction that it collides with another chlorine atom, then you can form a chlorine-chlorine bond, creating diatomic chlorine, and then that will be able to break the bond to the blue atom in the illustration. But if you simply flip that blue, green, red molecule around such that the collision of the independent green chlorine atom is colliding with the red atom, then that's not a collision, that's not an interaction between the green and the red that's going to result in a new bond. So those two particles would hit, maybe sufficient energy, but it's not the right orientation, and they're just going to bounce right off. When we talk about what is that sufficient amount of energy, the minimum amount of energy that's needed for a reaction to occur is what we refer to as activation energy. And so that is the energy that's needed at the very least to break the existing bonds that are present. Usually we refer to that as E sub A. If the energy of any given collision is at least equal to or greater than that activation energy, then the potential is there that a reaction can occur. If the collision is less forceful than whatever that activation energy quantity is, then there will be no reaction. And both of these, especially the first one, are working under the assumption that you do have the proper orientation. Now we can monitor what's happening with a reaction with what's known as a reaction profile diagram, which you see illustrated here on the screen. And so what this is going to show us is the potential energy that is stored within the chemical bonds of the reactant particles, and that's typically on the left-hand side, so that first left-hand flat area. Then, as energy is added through the collision, okay, the potential energy increases. We climb that hill until we get to the very tip top, and at the very highest energy state that this system is going to be at is what we call the activated complex. That's also sometimes referred to as the transition state. And so if you look at the Lewis diagrams that are presented here, you can see that in that first reactant molecule, the nitrogen-carbon bond is beginning to break as we, as the energy, we climb that energy hill, all right, to get to the transition state. And when we get to the top there at the transition state, effectively what you have is that carbon-nitrogen bond, the carbon-nitrogen bond has broken and the carbon-carbon bond has yet to be formed. So like a ball sitting at the pinnacle of the hill, it really could roll either way. In that activated complex, the carbon-nitrogen bond could reform and you go back to reactants. or the carbon nitrogen triple bond portion could continue to flip, and you create a new carbon-carbon single bond to create that that transition. And so that transition state is very brief, it's very flighty, it's very temporary. You cannot bottle up an activated complex form of a molecule and store it on the shelf, for instance. That's not to be confused with intermediates, which it is possible for an intermediate in a multi-step mechanism that you can actually isolate that. So the energy, that minimum energy that's required to get from the initial potential energy of the reactants up to that activated complex, that transition state, that is your activation energy, or your E sub A. So if you have numeric values on your y-axis for potential energy, you can actually quantify what is that activation energy. So the reaction profile diagram is what's going to map out each step of the way as the reaction proceeds at different times, what's happening with the energy that's involved. And so in this diagram, we can see that our two reactants there, the blue and the yellow shape, as those particles collide, if they collide with sufficient energy, that sufficient energy has to be at least equal to the activation energy, which again we measure from the initial energy value for the reactants up to the peak of that curve, which is the transition state. All reactions are always going to have a hill to climb to begin with. Okay, it's not a ramp. It's not going straight up or straight from reactants to products. There's always a hill that has to be surmounted before you get to products. The other energy difference that we can measure here is the absolute difference in energy between the reactants and the products, and that's known as the energy of the reaction, or in more fancy terms, the enthalpy of the reaction. Energy is a lot of times referred to with a capital E. Enthalpy would be a capital H. That's a thermodynamic term that we'll encounter later on. And so to calculate the overall net energy of the reaction, we want to take the energy value, the potential energy for the product bonds, product compounds, minus the potential energy for the reactants. And you always want to go in that order, product minus reactant, because that will give you a value that has either a positive or a negative sign associated with it. If the product energy is higher on the diagram than the reactant energy is, which is not what's shown in this diagram, but if say the positions of the reactant and the products were switched, then when you take products minus reactants, you would get a positive delta E value. This is what we call an endothermic reaction. It means that overall energy has to be put into the system. This would be a system that would probably feel cold to the touch or cool to the touch because it's absorbing heat from its surroundings and taking it away from your hand if you're holding on to it. On the other hand, if we have a situation like we see in the diagram here, where the product energy is at a lower quantity than the reactant energy, then when you take product minus reactant, delta E is going to evaluate to a negative value. Whenever you have a negative energy of reaction, that's what we refer to as an exothermic reaction. It means that the system is losing energy, it's giving it up, and so if it's giving up energy, that would translate to feeling warm or hot to the touch, because the system in breaking and forming new bonds overall has a net effect of losing energy. So if we were given the task of drawing a reaction profile diagram, we need to know a couple things. We need to know the energy of our reactants and our products, as well as what is the energy of the transition state. So here you can see we have a set of axes already established for us. Below that we have some given information about the product energy, the reactant energy, and the transition state energy. So with any graph, you want to make sure that your axes are well labeled. You can see that the energies given are in multiples of 100. So let's see what we have on the y-axis as far as our divisions. And as it turns out, it works out very nicely that we can number each one as 100 kilojoules, increasing increments. So next is to draw the reaction profile based on that given information. We've labeled the axes. So we start with our reactants. Our reactant energy is 200 kilojoules per mole. So we'd start by drawing a flat line at that location. Then our product energy at the very end is going to be 400 kilojoules per mole. So out at the right-hand side of the graph, I'm going to draw that line. Now, we want this to be, fairly symmetrical, it's just nice. It looks neater that way. So your transition state, you want to kind of split the difference between those two lines. Our transition state is at 900 kilojoules per mole. So this point right here is going to be where that hill peaks, if you will. So then we draw a smooth curve going from the reactant energy level to the product energy level, passing through that transition state point. And so there would be your reaction profile diagram that satisfies part A here. Second question, part B, is this reaction endothermic or exothermic? And then explain. Well, if we take a look, we see that the product energy on the right at 400 kilojoules per mole is higher than the reactant energy at 200 kilojoules per mole. So again, we look at, for endothermic versus exothermic, we look at delta E, not E sub A. Okay, so delta E is products minus reactant energy, and so that's going to be 400 minus 200. That gives us a positive value, so therefore we would say it's an endothermic reaction. And so again, our explanation, our justification could rest on either citing that energy of products is greater than energy of reactants, or that delta E evaluates to be a positive value. Question C then wants to know specifically what is the delta E, and we already talked about that. The products minus reactant energy is going to be 400 kilojoules per mole minus 200 kilojoules per mole for a grand total of positive 200 kilojoules per mole. Notice the sign is included, and that's because delta E can possibly be either positive or negative. So you do want to explicitly show the sign for delta E. Activation energy, on the other hand, is always going to be a positive value because every reaction, endothermic, exothermic, fast, slow, doesn't matter, is always going to require an input of energy to break the existing bonds. So what is the activation of the forward reaction? We take the energy from the reactants at 200, and we go all the way to the tip top of that profile curve to where our transition state is, and that would be at 900 kilojoules per mole. So subtract the two, and we would come up with 700 kilojoules per mole. Next up in your notes, you've got two examples to try here, so I invite you to pause the video, try these two out, graphing them and answering the following questions. Then you can unpause the video, resume, and check your work. So here are your solutions for the first example. And here are your solutions for the second example. Now, I think it's pretty safe to assume that it's common experience that when you heat things up, they tend to happen faster. Well, the same is true, if we're dissolving sugar or dissolving salt in water, or if we are undergoing a chemical reaction, in a beaker in a laboratory. We heat them up, things tend to go faster. All right, and generally speaking, as temperature increases, the rate of a reaction increases. If you've ever played around with glow sticks or glow necklaces and you wanted to prolong them, keep them around longer, so to speak, you might have thrown them in the fridge or the freezer. It doesn't stop the reaction, but the glow will tend to last a little bit longer. Might be a bit dimmer, but it does last longer. And so if you remember, the rate constant, which is represented by K, is temperature dependent. So when you change the temperature, K is going to change as well. And so if you recall the magnitude of K, the bigger K is, the faster a reaction goes. The smaller the K value is, the slower the reaction goes. So it stands to reason that when you raise the temperature of a reaction, that reaction's reaction rate constant, K, is also going to increase. And generally speaking, as a rough rule of thumb, the K value will double approximately for every 10 degrees Celsius temperature rise that you have in a given reaction. So if we look at the reaction that we've been looking at for the reaction profiles, you can see that the reaction rate for that process starts to grow very rapidly for every 10 degrees Celsius rise that there happens to be. So how can we relate the rate constant K to the activation energy of a reaction? Well, we talked about the effect of raising temperature and what that's going to do to the rate constant. But if we think about the magnitude of that hill that has to be climbed, the taller the hill is, the more energy is required. The more energy there has to be in that collision, that means fewer of the different collisions that are occurring are actually going to be effective collisions. So that means you're going to have very few products formed. It's going to be a very slow reaction, and slow reactions correspond to low K values. So if you have a large activation energy, that results in fewer effective collisions, which means a slower reaction and hence a small K value. Conversely, if you have a short hill to climb, there's a low activation energy. That means more collisions are going to have sufficient energy, so therefore you're going to have more effective collisions. The more effective collisions you have, the faster the reaction is going to go, and hence you would expect a larger K value. So activation energy and rate constant have an inverse type relationship with one another. Now, if we think about the distribution of the molecules and their motion and their kinetic energy, what you see here is, again, a Maxwell-Boltzmann distribution diagram, which shows that for any given quantity of molecules, okay, if we change the temperature, what happens is more of those particles have a higher kinetic energy, and it has the effect of shifting the distribution curve to the right. The area under the curve is constant, the number of molecules is constant, so the area under each curve has to stay the same. And what happens is that the overall distribution curve gets shorter and broader. What that does is that puts a greater proportion of the curve, the molecules that are underneath that curve, beyond the activation energy. So again, increase the temperature, particles have more kinetic energy, they're going to be able to have more effective collisions. Raising the temperature does not change the activation energy. It changes the energy of the particles and their collisions and enables more of them to hit that threshold. All right, so it's important to remember that raising temperature has no effect on activation energy itself. There are things that can affect the activation energy for a given reaction, but we'll talk about those in the future. All right, for a given reaction at different temperatures, the activation energy is going to be the same, but the K value is going to change. And so we're going to be able to use that changing K value with changing temperatures in a way that we can actually now we can relate and find the activation energy of a given reaction when the temperature is being changed. We can do it one of two ways. We can do it graphically, or we can modify that Arrhenius equation if we know a couple of data points. So the Arrhenius equation is the one that you see here. Rate constant is equal to A, which is known as the Arrhenius constant, times E, the numeric E, raised to a power that's equal to negative activation energy over RT, where R is the ideal gas constant and T is the temperature in Kelvin. And so by using some logarithmic identities and doing some rearranging, we can get this equation into a form that's in slope-intercept form, into that very familiar y equals mx plus b form. And so we can see that our y value would be natural log of k, the rate constant, and our x value that we're plotting it against would be inverse temperature. So that tells us what we need to plot, natural log of rate constant K versus inverse Kelvin temperature. And so when we do that, we get a linear relationship. Again, it's y equals mx plus b form. If we wanted to know the Arrhenius constant, A, we could calculate that because we see that shows up in the y-intercept portion. But more importantly, at this point, we're interested in being able to determine the activation energy. And so the slope of that line is equal to the negative of activation energy over the ideal gas constant. And the form of the ideal gas constant we're using is 8.314 joules per mole Kelvin. So if we have the measure of that slope, we can plug in our R value, we can rearrange and solve for what the activation energy would be. We can also determine the activation energy if we happen to know two data points. So for the same reaction, if we know the temperature that those reactions are occurring at, as well as their corresponding rate constants, then by modifying that Arrhenius equation, we get this equation, which might look a little intimidating, but again, you can use some logarithm identities here. You're just going to plug in the rate constants. You can simplify that before you take the natural log. The temperature portion there, just make sure that you evaluate inside the parentheses first with those inverse Kelvin temperatures. And again, rearrange to isolate and solve for E sub A, and you can get the activation energy value calculated from that. So whether it's graphically or from a table of data, there are ways that you can determine what the height of that energy hill that we looked at on the reaction profile diagrams would be.